So the grade covers quiz, 60%, final, 40%. So quiz usually takes 1 to 2 hour quiz. And let me see. So I will happily announce the very first quiz on April 16th. So topics will be from the beginning to whatever the topic we covered until the previous week of the quiz. And it's going to be 2-hour quiz. And you can prepare 2-page cheating sheet. Of course, one-sided and handwritten. So that you don't have to memorize all the formulas or maybe the derivation as well. So I'm not going to ask for the derivation or proof part, but maybe mainly focusing on the application of the mathematical theory that we learned throughout the class. So officially, cheating sheet is allowed. Cheating sheet in Korean is konning paper, right? So you can prepare A4 size, two A4 size cheating sheets, and then you can write down whatever the material that you like. But one thing that the magnifier is not allowed. No magnifier. So that means that your handwritten, the cheating sheet should be readable, legible by the bare end or with the glasses eyes. So any questions about the quiz and grade policy? Good. So we will continue the discussion. So I think we partially covered the inner product, right, in the last online class. So say we have x vector so this is basically 1 by n column matrix, but sometimes we write down as a vector. So when we say in my class, so vector has two different meanings. One is the real vector, the quantity that has a direction and magnitude, which is going to be covered probably the later part of the class, or maybe next semester, or the 1 by n oh my goodness, this is n by 1 actually. So the first letter is number of rows and the second letter is number of columns. So column matrix or vector, or sometimes called cat vector, or simply cat. And we also define the transpose operation of a cat vector. So the transpose of a cat vector. So transpose is x1, xn. And then if you take the complex conjugate on top of this transpose, after this step we take x transpose and complex conjugate, x1 complex conjugate, xn complex conjugate, which is actually defined as a joint operation. This is a name called adjoint operation. And when you have a column vector and you take the adjoint operation, then the result is denoted as a row vector. So we define x adjoint, which is x1 complex conjugate to xn complex conjugate. And sometimes we call this as a dagger. So joint operation, or sometimes we call it dagger. So if you take a magnifying glass, this looks like something like this, and this, and this. The dagger is like a short sword, right? And we define the inner product with the row vector and column vector such that inner product is defined as between column vector x and y equal with the parenthesis x and y, and which is actually defined as simply bra vector multiplied by the cat vector, which is x1 complex conjugate, xn complex conjugate, y1, yn is defined as x1 complex conjugate y1, x2 complex conjugate y2, xn complex conjugate yn. What happens if we change the order between x and y? Y, x is y, x, right? Then you just simply interchange the x and y. Then it is y1 complex conjugate x1 plus y2 complex conjugate x2, yn complex conjugate xn, which is same as x1 complex conjugate y1, xn complex conjugate yn, and complex conjugate, which is x and y complex conjugate. So when you change the order, then you just put the simply complex conjugate on each other. It's one of the basic properties of the inner product for the matrix. So simply didn't make any mistake. X and y is same as y and x and complex conjugate. if you have some like a matrix in between, we have X and we have some matrix A and some matrix Y, which is same as X and we have A, Y, right? What happens if we take the complex conjugate? Which is same as Y, A, dagger, X. We have shown previously that when you do matrix multiplication of two matrices, when you have A, B transpose, what do you have? B transpose, A transpose, right? So A transpose, Y transpose is, no. Transpose is Y transpose, A transpose, right? And when you take the complex conjugate, transpose, complex conjugate, Y transpose, complex conjugate, A transpose, complex conjugate, and what is the transpose of vector with the complex conjugate? This is a bra vector, right? So this is Y. This is Y. Oh, what happens? Okay. This is Y, A, there you go. Therefore, we have X, A, Y conjugate is same as Y, A, dagger, X. Let me just double check your background. Anybody who hasn't learned about the matrix, raise your hand. So you haven't taken any class in matrix in high school? How about in freshman? No? Okay. Actually, I found there is one from the see. There's one student from the English literature, Duvora, attending the class. Raise your hand. Oh, so have you taken the calculus or matrix? 미적분학 혹은 행렬 배웠어요? Okay, so perhaps you have to study really hard. Because after this matrix class, we will be involving heavily with the calculus. How about in France? Have you taken calculus?
Yes.
You did, right? How about the matrices?
Matrix.
Yeah. You did. Good. All right. So if you think I'm going a little bit fast, one of the best way to delay the progress is asking a question. So you can actually ask a question in Korean too. I mean, this class is supposed to be English class. Official language of the class is English, but I mean, I can pretend that, I mean, if you can ask me a question in Korean, if you're not quite confident with speaking English. Am I loud enough? So you have any trouble understanding, listening? Okay, let me. that's the inner product. There is another class called outer product. Probably, or most likely, then most of you haven't learned about this product, which is defined as the following: X this way. You wrote the cat vector first and then bra vector later. This is called cat. This is called the bra vector. So cat vector and bra vector, the origin of the notation is actually from this symbol. This is, in English, what do you call this? Bracket. This is called the bracket. What is this? Parenthesis. Parenthesis. What is this? Brace. So in Korean, I think the parenthesis is called 괄호, and brace is called 중괄호. But bracket, I don't know. What do we call this? This. The bracket, actually, you cut in half. So this part is called the bra, and this part is called the cat. So the definition of bra vector and cat vector actually originated from 1925, first denoted by 1925, Paul Adrian Maurice Dirac, the famous English physicist who got the Nobel Prize in 1920 something. So he introduced the bracket notation. So anyway, x1, xn, y1 complex conjugate, yn complex conjugate, x1, y1 complex conjugate, x1, yn complex conjugate, xn, y1 complex conjugate, xn, yn complex conjugate. So this is n by n matrix. So inner product and the outer product is quite different effect. Inner product, you take two vectors, and then the final result is the scalar. You get the scalar, in general complex scalar. On the other hand, the outer product, you take two vectors, and you produce n by n matrices. So the major difference is the following. Okay, so inner product, which is x, y. So take two vectors and produce a scalar. Outer product, on the other hand, the initial part is the same. Take two vectors. And produce n by n matrix. So let's do some practice. Say we have a lambda 1 vector, square root of 2 1, 1. Lambda 2 vector, square root of 2, 1 minus 1. Let's say lambda 1 is equal to plus 1, lambda 2 is minus 1. This part we will come to later, but let's just set this way. Just set this way. More about this will come later. More will come later. Let's just do some practice. How about x lambda 1 and lambda 1 in a product? So we have square root of 1 over square root of 2, 1, 1, right? And 1 over square root of 2, 1, 1. So that we have 1 over 2, 1, 1 times 1, 1. What do you get? If we multiply this and this, what do you get? 2. So we have 2 is equal to 1, right? Very simple. How about lambda 2 and lambda 2? Which we defined as a square root of 1 over square root of 2, 1 minus 1, square root of 2, 1 minus 1. So we have 1 over 2, 1 minus 1, 1 minus 1, which is 1 over 2. If you multiply by this 2, what do we have? 2, right? It's 1. How about if you have two different index? Lambda 1, lambda 2. Square root of 2, 1, 1. 1 over square root of 2, 1 minus 1, which is 1 half. And if you multiply by this and this, what do you get? Which is 1 minus 1 is equal to 0, right? Very good. 0. How about 2, if we have a order interchange, interchange it, lambda 2, lambda 1, which is same as actually lambda 1, lambda 2 complex conjugate. And this is real number, so complex conjugate is same as the itself, which is 0. So we found that inner product with the same index is 1, right? How about the inner product with different index? 0. So this is called orthonormal. We say this is orthogonal. And we can put this as a lambda 1, lambda 2 as an orthonormal basis. For two-dimensional vectors. Vector space. What about the out product? Lambda 1, lambda 1. Let's do some practice. One is square root of 2, 1, 1. Square root of 2, 1, 1, right? So it's 1 half. you just multiply this 1, 1, 1, 1. Lambda 2, lambda 2. Square root of 2, 1 minus 1. Square root of 2, 1 minus 1, which is same as 1/2. You just multiply 1 by everything here. So it's 1 minus 1. And second line is opposite. Minus 1, 1, right? So very interesting property is if we add them together, what do we get? One half, 1, 1, 1, 1, plus 1/2, 1 minus minus 1, 1, which is 1, 0, 0, 1, right? Which is called identity matrix. So if you have a normal orthonormal basis, and if you form the outer product and sum together, then we obtain the inner product, the identity matrix. So we can actually generalize it. I made any mistake? Lambda 1, lambda 1. If there's an orthonormal basis of, in general, it's n-dimensional vector space, then two things. Identity. Here, IN is 1, 0, 0, 0, 1, 0, 0, 1, which is n by n. So this is very useful, the mathematical properties of orthonormal basis that we are going to utilize. So let's do some other example, just in case. Let me check. Say one I complex number. Lambda 2 is square root of 2, 1 minus I. And say lambda 1 is plus 1, lambda 2 is minus 1. What is the inner product between two vectors? I think this is just 2 by 1 matrix, so maybe good for the mental exercise. Square root of 2, 1. You have to take the complex conjugate when you change the cat vector to bra vector, right? So this is minus I, square root of 2, 1I. What do we get? 1 over 2, you get this. 1 minus I square. I square is minus 1. We have I square is minus 1, right? So minus I square is plus 1. Is equal to 1, right? Lambda 2, square root of 2 is now opposite. We have I, square root of 2, 1 minus I. One over 2. If we multiply this together, 1 minus I square is again 2. 1 plus 1 is 1, right? How about lambda 1, lambda 2? Square root of 2, 1 minus I, square root of 2, 1 minus I, right? So we have 1 over 2, and you multiply them together, 1 plus I square, which is 0, right? Which is same as 1 minus 1 is equal to 0. And which is same as lambda 2, lambda 1, and conjugate. So we found that this, again, this factor is orthonormal basis. And so let's check whether the outer product satisfies the same condition. Made any mistake? Right. One over square root of 2, this is I. 1 over square root of 2, this is minus I, right? So if we 1 over 2, 1 minus I, 1, right? How about lambda 2, lambda 2? Square root of 2, 1 minus I, square root of 2, 1I, which is 1 over 2, 1I minus I1, right? So if we add them together, what happens? Lambda 1 is equal to plus lambda 2 is equal to 1/2 1 minus I1 plus 1/2 1I minus I1, which is same as 1001, right? Which is basically the identity. Since we set the lambda 1 and lambda 2 as plus and minus, let's see what happens. Lambda 1 plus lambda 2, lambda 2. We said this is plus 1, this is minus 1. I mean, I didn't say why I put lambda 1 is equal to 1 and lambda 2 is minus 1, but it's going to be more obvious later, I mean, if we progress to the next topic. But now, just assume the number is just given by 1 and minus 1. Then what happened is 1/2 1 minus I1 and minus 1/2 1I minus I1. So which is actually 0, minus I 0, right? And this matrix is a name called sigma y, and we call this sigma y. And let's go back to the previous case when we said 1, 1, minus 1, minus 1. How about, am I going a little bit too fast? Do you need the time to copy, or is it okay? Not too fast, hopefully. 이거 왜? The screen is out. So let's just wait a few minutes until we reboot the system. 병영이 불러봐. 병영이가 잘하는 거. Do not know the reason why the projection is off. It's supposed to be on. And in English, there is one particular, the expression for this kind of situation is called Murphy's law. If something is going to go wrong, it will go wrong. So it actually happens once in a while, but I hope not too often. 지금 켜졌나?
누르긴 했는데 켜졌는데 시간이 걸렸어.
왜 꺼졌지? Okay, thank you. So we are in good shape. And, oops. Let me see. What about in case lambda 1 was square root of 2, 1, 1, lambda 2 was square root of 1 minus 1 with lambda 1 is plus 1, lambda 2 is minus 1. Then lambda 1, lambda 1, lambda 1 plus lambda 2, lambda 2, lambda 2 is plus 1, 1 half, 1, half, 1 minus 1, 1 minus 1 is 1 half, 1, 1, 1, 1, minus 1 half, 1 minus 1, minus 1, 1, 0, 1, 1, 0. It has another name called sigma x. Or we can set another different vectors. example 3, when you have set one, the simplest case, lambda 2, 0, 1. Then obviously they are, and say lambda 1 is plus 1, lambda 2 is minus 1. They obviously, lambda 1 and lambda 2 are orthogonal to each other, right? So we don't have to show, but this shows that this is orthonormal basis. So lambda 1, lambda 1, lambda 2 is 1, 0, 1, 0, 0, 1, 0, 1, which is 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, right? Which is identity. How about plus 1, lambda 1, lambda 1, minus 1, lambda 2 is 1, 0, 0, 0, minus 0, 0, 0, 1, 1, 0, 0, minus 1, which is another name called sigma z. In quantum mechanics, these three matrices are called Pauli matrices. In quantum mechanics, the matrices sigma x, sigma y, sigma z are called Pauli matrix. And they also play significant roles in quantum computation. So probably you have heard about quantum computation, right? One way or another, newspaper or whatever. In quantum computation. So sigma x 0, 1, 1, 0, sigma y 0 minus I 0, sigma z 1, 0, 0, minus 1. And in quantum computation, this matrix, we say this is zero vector. I say put 1, 0. This is called quantum bits, or sometimes called qubits. Then interesting property is, if you apply Pauli matrix sigma x, what do you get? 0, 1, 1, 0, 1, 0. You get 0, 1, right? Which is 1 vector. Or sigma x 1, 0, 1, 1, 0, 0, 1, which is actually 1, 0, right? So this is, so sigma x is actually equivalent to NAD operation, which is what? This is called NAD operation, right? So sometimes, so sigma x is equal to just big X. Perhaps you can take a break for a few minutes. Okay, so any questions? I seems to have a tendency to go a little faster as I progress. So if you think I'm going too fast, just let me know. So I'll try to slow down as much as possible. Now let's think about the eigenvalue problems now. Eigenvalue problem is the following problem. A times x is lambda times, probably it's better to use the same jargon. And we call this is eigenvector. And this we call this eigenvalue. So the question is how to solve this problem. So we actually change this problem in this way. A lambda minus lambda by lambda is 0, right? Or A lambda, but we can say lambda times I matrix, lambda is 0, right? Or A minus lambda I, lambda is equal to 0. So we ask the following question. What if determinant of A minus lambda I is non-zero? For this problem, if determinant A minus lambda I is non-zero, what happens?
Inverse matrix?
Yeah, correct. So inverse matrix exists, right? Then, obviously, A minus lambda I inverse exists. So A just repeat myself. A lambda is lambda lambda. This is eigenvalue problem. And if we, from this we have the following equation: A minus lambda I, lambda is equal to 0, right? So if determinant of A minus lambda I is non-zero, then the inverse matrix, right? The inverse matrix matrix A minus lambda I inverse exists. If the inverse matrix exists, what happens? We can find lambda, right? Then lambda is A lambda inverse times 0, right? Which is 0. So when determinant A minus lambda is non-zero, then we have all the trivial solution. The trivial solution exists. So if we like to have a non-trivial solution, what will be the condition? Determinant is equal to 0, right? So when determinant of lambda minus A minus lambda I is non-zero, then the zero solution is called trivial solution exists. It's trivial. So for non-trivial solutions, what will be the condition? Determinant has to be 0. Okay, I'll go a little bit slow. So for non-trivial solution, we should require determinant of A minus lambda I is equal to 0. So that's the reason why you learned about determinant first, beforehand. So let's consider some example. A is one of the Pauli matrix. A minus lambda I 0 1 1 0 minus lambda 1 0 0 1, which is minus lambda 1 1 minus lambda, right? So what is the determinant? A minus lambda I is determinant of minus lambda 1 1 minus lambda, which is lambda square minus 1. A11, A22 minus A21, A12, right? So which is equal to 0. So lambda is plus 1 or minus 1. So it's a hint that we have considered some particular number called 1 and minus 1 in previous examples, right? So, and also matrix is somewhat familiar. This is a Pauli matrix, sigma x. So which is sigma x. In Greek letter is called sigma. It's probably you know about sigma, right? So throughout the class, I may use some Greek letters. So say alpha, beta, gamma, delta, epsilon. There are 24 alphabets. So you can check out the Wikipedia or Google. And blah, 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 sigma, etc., etc. The last word is omega. So Greek letters from alpha to omega. So how do we calculate eigenvector? Then we substitute back to the original equation. So to calculate the eigenvector, we substitute eigenvalue to the original equation. So for example, say when lambda is equal to 1, say like this is equal to lambda 1, then A lambda 1 is called plus 1 lambda 1, right? And we don't know lambda 1, so we can set lambda 1 as A and B. Then A was 0, 1, 1, 0. So 1, 0, 1, 1, 0. A and B is same as A and B, right? So what do we have? B is equal to A, right? So lambda 1 is simply AA. And then we make this normalize. We set lambda 1 is equal to 1. This is called a normalization. In Korean, they say 규격화, right? So lambda 1 is generally, so A is generally complex. So A complex, A, which is twice of A squared, is 1. So we have actually the freedom of choices, but we can set A as the square root of 2, 1 over square root of 2. Then we have lambda 1 as 1 over square root 2, 1, 1, right? And of course, lambda 1 is equal to plus 1. For lambda 2 is minus 1, and let's say we can set lambda 2 as C and D, then A lambda 2 is minus lambda 2, right? Because we set the lambda 2 is equal to, we found that lambda 2 is minus 1, so 0, 1, 1, 0. CD is minus over CD. So what do we have? D is equal to minus C, right? So lambda 2 is C minus C. And if we require from lambda 2 is equal to 1, we can set C as square root of 2. So lambda 2 is 1 over square root of 2, 1 minus 1. Now we go back to the original, the examples we studied before beginning of this class, right? We can double check the lambda 2. We have already checked that lambda 1 is equal to 1, lambda 2 is equal to 1, lambda 2 is equal to 0, and lambda 1 plus lambda 2 is called identity. This is called completeness property. And lambda 2 is what? This is sigma x, this is A, right? It's very interesting that the outer product, together with the eigenvalues, produce the ordinal matrix. This is actually true only when A is Hermitian. This is true for Hermitian A. And this is a name called spectral theorem. So when we have a Hermitian matrix, then we have the following spectral theorem. This is very powerful mathematical property. So, any questions? I was wondering if the spectral theorem was also in the math, the swap class in swap. In your math. 수학 과학생이 있었는데 이거 스펙트럴 theorem 배웠어요? Okay. If not, then it's probably good time to learn. So later I'm going to tell you the spectrum is a very powerful property that you can represent matrix functions using this spectral theorem. So when A is Hermitian, then there are several properties. That is, eigenvalues are real. Second, eigenvectors are orthonormal. Third, the completeness property. Yes. 4, spectral theorem. Okay, I'll let you talk. This is a very important part, and also very important for quiz. These 4 properties. Let's consider the special case when A is Hermitian but with a complex entity. When A is 0 minus I 0. This is actually sigma y. Let's check when A transpose is. What is the result of the transpose? Transpose is you interchange a row with a column, right? So this is I minus I 0, right? And when you take the complex conjugate, it becomes 0 minus I 0, which is A dagger, but which is same as the original matrix A, right? So we call A as Hermitian matrix. Therefore, A Hermitian. So let's try to find out the eigenvalue problem. Eigenvalue. Example 2. So A lambda is equal to lambda lambda, right? So A minus lambda I is equal to 0. A minus lambda I is minus lambda minus I minus lambda. So what is the determinant? Determinant A minus lambda I is this, minus lambda minus I minus lambda is again lambda square minus 1, right? Because I square is minus, right? So plus I square is minus 1, so equal to 0. So lambda is again 1 minus 1. Lambda 1 is 1, lambda 2 is minus 1. Somehow, I have a feeling that we encounter the same vectors that we studied in the beginning of today. But let's just check what happens. So set case 1, lambda 1 is plus 1. Then say A, B, right? So lambda 1 is lambda 1. So 0 minus I 0, AB is equal to AB. So that is B is AI, right? Correct? So we have the following. Lambda 1 is AI. So lambda 1 is what? A minus A complex conjugate, A complex conjugate, AI, A square plus A square equal to 2A square is equal to Y. So we can check A as, we can also set, we can set A is 1 over square root of 2, right? So A is actually arbitrary, so we can choose whatever 2A square is equal to 1. So we can say lambda 1 square root of 2, 1I. Familiar? Somewhere today we covered this, right? we set this factor. What about minus 1? And let's say lambda 2 as a C and D. Then A lambda 2 is called minus lambda 2. 0 minus I 0. C and D is minus of C and D. So that means D is minus Ci. So lambda 2 is actually C minus Ci. And set lambda 2 is equal to 1. We have C is 1 over square root of 2. And we have lambda 2 is square root of 2, 1 minus I, right? Very interesting property. Then what happens? Lambda 1 minus lambda 2, same as this one, right? 0 minus I 0, which is A. So we check that. We have already derived this result previously, and it says this is a result of the spectral theorem. So far, the problem we considered has eigenvalue as plus and minus, right? Plus 1 and minus 1. There are some particular matrices. Positive Hermitian. Positive is eigenvalues are all positive. We call positive matrix when the eigenvalues are positive. So this is one of the special case. Say M 125, 125, minus 75, minus 75. So try to find out this matrix. Oh, sorry, lambda. So determinant of m minus lambda I, determinant of 125 minus 75, 125 minus lambda minus 75, which is what? 125 minus lambda square minus 75 square is equal to 0, right? So, or 125 plus 75 minus lambda, 125 minus 75 minus lambda is equal to 0, right? So 200 minus lambda, 50 minus lambda is equal to 0. So lambda is 50, 200. So in this case, eigenvalues are all positive. We set m, yeah. Since the eigenvalues of m are all positive, M is a positive matrix. Also Hermitian, and also Hermitian. And also Hermitian. Let's try to find out the eigenvector. So say lambda 1 is 50. Then m AB, m lambda 1 is 50 lambda 1, right? So 125 minus 75 minus 75, 125 AB is 50 of lambda 1 AB. So 125A minus 75B is 50A minus 75A plus 125B is 50B. So what do we have? A is equal to B, right? Right? So we can say lambda 1 is square root of 2 without right? Same as before. How about 200? Original matrix, right? So lambda 2, C and D, M lambda 2 was 200 lambda 2. So 125 minus 75 minus 75, 125. C and D is 200 and C and D, or 125 AC C minus 75 D minus 75 C plus 125 D is same as 200 C 200 D. So that means D is equal to minus C, right? So we can just write down the lambda 2 as before, square root of 2, 1 minus 1, right? For this matrix, I mean, you can easily see that the completeness is satisfied. How about the spectral theorem part? So let's check the, I think I'm going a little bit fast. Seems like I'm losing your attention. So we are going to check the spectral theorem. lambda 1, lambda 1, lambda 1, right? Plus lambda 2, lambda 2, lambda 2. So lambda 1 is 50, so 50 and 1/2, 1, 1, 1, 1, plus 200, 1/2, 1 minus 1, 1 minus 1, which is 50, 1/2, 1, 1, 1, 1, plus 1/2, 200, 1 minus 1, minus 1, 1. So that is 25, 25, 25, 25, plus 100, minus 100, minus 100, 100, which is 125 minus 75, minus 75, 125, which is same as M. One of the nice things about spectral theorem is we can actually represent square root of M. Using spectral theorem, square root of M can be written as a square root of lambda 1, square root of lambda 2, this way. So we are going to prove this property later, but just write it down, the result, and check if it works. So this is square root of 50. This is 1/2, 1, 1, 1, 1. Square root of 200, 1/2. This is 1 minus 1, let me see. Minus 1, 1. Square root of 50 is what? 25 times 2. So 5 square root of 2, right? How about square root of 200? 200, right? So it's 10 square root of 2. So this is basically 2 over 5 square root of 2, 1, 1, 1, 1, plus 2 over 10 square root of 2, 1 minus 1, minus 1, 1. So we have, so this is 5, right? We have 2 over 15 square root of 2, 2 over 15 square root of 2, and this is minus, which one? 2, minus 2 over 5 square root of 2, 2 over minus 5 square root of 2. And let's check if this actually works. So I'm going to multiply by this together. Copy. And next page. Paste. This is very nice. Which is this. So checking, recheck. If this is indeed a square root, so multiply them together. 2 over 15 square root of 2, minus 2 over 5 square root of 2, minus 2 over 5 square root of 2, 2 over 15 square root of 2, same thing, 2 over 15 square root of 2, minus 2 over 5 square root of 2, minus 2 over 5 square root of 2, 2 over 15 square root of 2. So multiply them together, what happens? We have 2 over 15 square and multiply by 2, right? Oh. Again. So looks like Murphy's law is hitting us again. And I'm going to put this my class on YouTube tonight, so you can check. 시간이 되면 꺼지나 보다. 켜졌어.
기계는 켜졌어.
Okay. So it looks like a projector is automatically shut down in every 50 minutes. I don't know why, but minus 4 over 25 times 2. Is it? It is square. And this is 2 over 15 square times, this is square, times, this is second product is minus 4 times 75 times 2 minus 4 by 75 times 2, right? So this is actually minus 75. And this part, let me see, which is 4 over 225 times 2 minus 4 over 50. Let me see. 50. So 225 times 2 is 450. Minus 50 is 200. Let me see. Something is wrong. This and this. 4 over 25 times 2. 4 over 25 times 2. 450 minus 50. Oh, this is plus. This must be plus, right? So plus. So that is 125. So we have minus 75, 125, which is same as m, right? So we have shown that this is indeed the square root of the matrix M. So this is actually square root of m. So spectral theorem actually allows to calculate the functions of matrix. And so probably we are going to delve more into this topic next week. How about that? So I think we have covered maybe a little bit too much material for one day today. So I'm thinking about stopping here and continue the discussion next week. Is it okay? All right. So I'm going to put this class on YouTube tonight. It'll be nice if you like it, the YouTube. Yeah, check the like. All right. Thank you.